about him. Antonio Acin is an ICREA research professor at SECPHO, and he's a physicist and a telecommunication engineer from the Polytechnic University of Barcelona. He got his degree in theoretical physics, so he is very well renowned for his research as a theoretical physicist. And he did a postdoctoral research state in Geneva. He joined ICPHO in 2003 as a group leader, where he is in charge of the quantum information theory group. His research interests range from quantum information theory, quantum thermodynamics, quantum optics, and he is also a great expert and has been pushing all the quantum technologies forward during the recent years. And since 2016, he holds the AXA chair for communication for quantum information science. So now, Antonio, I'll let you the role as presenter, and please show us what you have to tell us.
Okay, so can you hear me?
Yeah. Yeah.
Okay, good. So
Perfect.
I will now share my application. I just want to, of course, thank you for the invitation. And as we discussed, the idea was that I somehow provide an introduction to the field. And can you see my presentation now?
Yeah, everything all right.
Okay. Okay, so as we discussed, the idea was that I give a sort of a general introduction to the field, explain a bit the context motivations, and then my colleagues will somehow expand over my rather basic introduction. Okay, so then I chose this title because these are terms that are nowadays used, like quantum information technologies and the second quantum revolution. And so before, I don't know why. Okay, yes. So before going into that, I should first explain what was the first quantum revolution, and this is something that happened around at the end of 19th century, beginning of 20th century, and it was mostly done by physicists. And basically, what they did, they wanted to understand what happens when you move from the macroscopic scale, I mean our scale where we apply Newtonian physics, to the microscopic scale where you have atoms and electrons and atomic particles. Okay. And what they saw is that physics behave in a different way, and then they had to invent a new formula, and that was quantum physics. Okay, so it was just somehow scientists, and mostly physicists, they were pushed by experimental observations, and they had to change the way we reason about nature, and they invented a new theory, which was quantum physics. Now, perhaps the interesting thing was that quantum physics is really a revolution because it changes many things, and in particular, our understanding of how nature behaves at this scale. And this is because in quantum physics you have some phenomena that somehow are, at first sight, I would say they are not easy to appreciate with our classical intuition. So the first thing is quantum superpositions. I guess many of you know about it, but I would say a few words about it. So the quantum superposition, what happens for quantum physics, is that you may have a particle that is in a state. So in this situation, I describe this particle as being on the right-hand side between these two possible positions. Of course, you can also have the particle be in the left-hand side, but then quantum physics tells you that that this particle can also be in the superposition of the two positions. And here I represent a symmetric configuration, but there might be also asymmetric configuration where there is more weight on the left-hand side with respect to the right-hand side. And I would like you to understand that these superpositions is something different from the particle being here or there with probability 1/2. So it's something different. And well, these superpositions have been demonstrated in the labs. Of course, they somehow are, you may have problems to understand them if you move this concept of superposition to our scale, because we all know about the Schrödinger cat that can be alive or dead. But leaving aside what happened, how to deal with superpositions in our scale, what is true is that atoms, they can be placed in superpositions. Okay, so in all my talk, I'm going to focus in the microscopic scale. I'm not going to talk about cats, but I'm going to talk about atoms, and atoms can be in superpositions. And also because of these superpositions, we have another phenomenon that is also well known. We have many. I'm just choosing here superpositions, and the other phenomenon I'm choosing is the uncertainty principle. that tells us that if you measure a particle, it can be perturbed by the measurement. Okay, so for instance, here, if I have this atom that is in superposition of being in these two places, and now if I measure whether the atom is in the left or right position, then I can have left or right with probability 50% probability. But what happens after the measurement is that the atom collapses into left and right. As you can see here, the state of the atom is not the same before and after the measurement. Again, this creates many problems, like understanding what is really, what is reality? Is it what I see in the measurement? Is it what was there before the measurement? But the fact is that nature behaves in this way for quantum particles. So this is what I want to emphasize here. These phenomena might be weird, but they describe how nature behaves at the macroscopic scale. So atoms, photons, they are described by quantum physics. So that was the first quantum revolution. It was a conceptual, here I'm focusing on the conceptual aspect, but of course the first quantum revolution was also a revolution in applied aspects. So we have many devices that we use today that are based on our understanding of nature through quantum physics. So for instance, lasers and transistors and semiconductors, all these critical applications were pushed by quantum physics. Okay, let's see here, receive an annotation. I don't know, what should I do? Okay. Okay, so now we are facing the second quantum revolution, and somehow what is happening is something similar to what we had 1 century ago. So that was the first quantum revolution. Again, we are moving from Newtonian physics to quantum physics. So now we are experiencing the same revolution, but now for information. So here, somehow the transition was for physics, and now we are doing the same transition, but now for information. So we are moving from classical information theory, which is what we use with our computers and our internet, our communication. And now we are moving to a new type of information theory that is of quantum nature. So we are experiencing a similar process now in the context of information technologies. And now why is this happening? There are several reasons. I think one of the reasons is that for the first time, we are able to control quantum particles. So before we were accessing the quantum world, but we could not really control the superpositions. We could not play with atoms. Now we can do that. And well, if you want to have a clear manifestation of that, if you look at the Nobel Prize in Physics in 2012, it was given to Serge Haroche and Dave Wineland because, as you can read here, they developed methods for measuring and manipulating individual particles, okay, with a lot of control. So now we have the control of manipulating and doing operations with individual quantum particles. And in particular, we can put information on quantum particles. So this can be done in the labs. Then from an applied point of view, our information devices are getting smaller and smaller. So here you have a picture of an old computer, and this is our smartphones, that are also small computers. And this miniaturization goes on, and we are now reaching the position in which we can also put information on quantum particles. So the question then is obvious: what happens? What is it going to happen when we put information on particles that are described by a set of laws, quantum physics, that are not the same as we have for our standard information devices based on classical physics? And then here is where the new concepts come. And just to give an illustration, well, the first thing we can do is to put a bit on a quantum particle. And what is a bit? A bit is something that can take two values. So here I'm encoding a bit on the atom before, so I'm putting a 0 whenever I would say that I encode a 0 whenever I put the atom on the right. Then I would say 1 when the atom is on the left. But because of superposition, it immediately follows that the quantum bit can also be in a superposition of the two values. This is just elementary quantum physics. The only thing I did was to put information on a quantum particle, and because of elementary quantum physics, then my quantum bit, called qubit, can also be not only in 0 and 1, but also in the superposition of 0 and 1. And then if you accept this concept, then you can start thinking about, okay, how can I manipulate information stored in quantum bits? And you can have interesting things like a quantum computer. So a quantum computer is the same as our classical computer. What is a classical computer? It's a device that manipulates information stored on classical bits. The quantum computer does the same, but for information stored on quantum bits. I always choose this example, which is a bit too simplistic, but it somehow shows some of the main ideas about quantum computation. Enrique Solano will discuss about this later. So imagine you had to compute the table of 2. So what you can do on a classical computer, you put here 2, you multiply by 1, and you have 2. You multiply by 2, and you have 4. And if you want the full table, you have to run your computer 10 times, and you have the whole table of number 2. Now, if you have a quantum computer, you can put the 2, and now you can add a superposition of 1 up to 10, and with just one call to the, there is a lot of noise, sorry. Okay. So with just one call to your computer, you can have the whole table in your output. Okay, and this is called quantum parallelism. You see here, I introduced a superposition of 1 up to 10, and at the output I have the table in a superposition. Okay, so this seems very good, and this is called quantum parallelism, and this gave hope that using a quantum computer you can solve problems more easily with a classical computer. Well, things are not that nice because you have to read the information, and as I was telling you, measurements destroy the information, the superposition. So for this particular case, if you measure the information, you will get sometimes 2, sometimes 4, sometimes 18, sometimes 20. So you lose this benefit for this particular problem. But somehow quantum computation is just the interplay between these two things. So you can play with quantum parallelism, this is good, and you have to do it in a way so that the measurement does not destroy this gain that you have here. In this case, I was not smart enough to play with these two factors, but sometimes you can. And the breakthrough in this case was obtained by Peter Shor, who proved that there is a particular problem that is called factoring, for which you can solve that can be solved more efficiently on a quantum computer. Okay, so what is factoring? So factoring is a problem where you have to find, given a number, you have to find 2 numbers that multiply give this number. Here it's easy, 2 times 3, but I can easily make the problem more complicated. So this is still easy. This is a bit more complicated, but I can make it very hard. So here you have to give me 2 numbers such that the product is equal to the number. This is difficult. And it's not only difficult for me, but it's difficult for any computer we have on Earth, including supercomputers like the Barcelona Supercomputer Center, because we don't know any efficient classical algorithm to solve factoring. While interestingly, factoring is easy for a quantum computer. So if you give this problem to a quantum computer, we don't have a quantum computer at the moment, but we can study what can happen with a quantum computer. Then the quantum computer can solve and find 2 numbers that are whose product is equal to the initial number. Now, if you think for a while about what I did here, well, I was solving this problem. You see, I was starting by this number, and I was computing 2 numbers, and you can see that the product of these 2 numbers is equal to the initial number. So how come did I do that? Because I was telling you that this problem is difficult. Well, I don't have a quantum computer, so the only thing I did, I was cheating. So what I did, I started by these 2 numbers, and I computed the product. But in my presentation, I was giving just the result. Okay, and this is because this is a situation of what is called a one-way function. It's something that it can be computed very easily in one direction. I can easily compute the product of these 2 numbers. While it's very hard to reverse, if I give you the result, it's very hard to get the 2 numbers whose product is equal to the initial number. So factoring is hard, multiplying is easy. And these functions, they may seem perhaps not so interesting, but actually they are, and they are using cryptography. So in cryptography, we have 2 parties who want to exchange a message, and then we have Alice and Bob. And for instance, factoring is used to secure our messages today. So there is a protocol called RSA, and basically what happens is that the honest parties, to run the protocol, they have to multiply. But the enemy, usually called Eve, if she wants to read the information that Alice and Bob are exchanging, she has to factorize. Multiplication is easy, factorization is hard, the protocol is secure. Now, if Eve has a quantum computer, she's quantum Eve, factorization is easy, so the protocol is insecure. So perhaps the most commonly used cryptographic protocol becomes insecure against an enemy with a quantum computer. Okay, so this is a risk that we have. Okay, and this is also gives a motivation to develop a quantum computer, among others. Luckily, quantum physics also gives us the solution to that problem, and this is quantum cryptography. So the idea here is that Alice and Bob encode information on quantum particles using quantum superpositions. And now when the eavesdropper tries to read this information, she perturbs the state of the particles. So Alice and Bob can notice that someone is trying to read information and they abort. Okay, so the eavesdropper, when measuring the particles, modifies their state and is detected. So this protocol can be proven to be quantum secure. Okay, this was just a super easy, fast introduction to some of the themes. So when you make this transition, then a revolution for information happens because you have more powerful computing devices. And of course, this is relevant for any problem, not only for factoring, but you have a more powerful computer. This is good. And we have a new form of securing messages through, quantum cryptography. We don't only have this, but actually we have more things. And now there are many efforts worldwide to understand what you can do when you encode information on quantum particles. So as it was mentioned, here in Europe, we have the Flagship. And the Flagship has been structured along these different directions. We have basic science. We have some sort of horizontal directions that go across the main applications. And the main applications are on computation, communication, on simulation, which is a form of quantum computation, and on sensing. So this is more or less sort of overview about all the activities. And in my presentation, I mostly focus on communication and computation, just giving you the main ideas for that. But I guess my colleagues will expand on that. And I think the horizon, at least for me, is clear. I believe that we go into a future where we'll have computer and communication devices that will use quantum physics. And with this, I stop with my presentation. Thank you very much.
Thank you, Antonio. Thank you very much. I don't know, Alex, if you want to make questions.
Hi, thank you very much, Antonio. Sorry, I was having troubles with the audio connection now. So thank you very much for the nice talk. I was saying that if any of the assistants wants to let us know some questions to Antonio, they can do it through the chat or they can directly tell it to me. In the meanwhile, I have personally a question. It might be maybe very technical, but I always hear about this problem of the factorization. But I really don't understand how could you, let's say, how could you engineer a device? How could you use quantum physics, quantum mechanics to solve this problem? Is due to entanglement? What's exactly the resource that you would exploit there to solve it faster? And what is the order of how it scales in, let's say, in classical theory to quantum information theory?
Okay, so well, the way you solve the problem is somehow the input to your problem is just a number that you have to factorize. Okay, so what you do, this number, you write it in classical bits, and you encode these classical bits on a quantum particle, like I was telling you. So if it's a 0, you say, I'm going to use the spin representation. So qubit, you can see it as a spin particle. So if it's a 0, you put the spin pointing up, and if it's 1, you put the spin pointing down. Okay, this is a classical bit that you put on a quantum particle with spin. And now you give this to the quantum computer. So the quantum computer will take this qubit and will create superpositions of these qubits. Okay, so it will. There is a process. It's a bit complicated for this talk. Actually, I must admit that I don't even remember how it works. But basically, the algorithm runs some operations on these qubits and creates superpositions. So I would say, for this particular case, it's more about the superpositions among the different qubits that makes gives the speed up. So factoring is one of these cases where creating the superposition, having this parallelism is good. And at the very end, this is not destroyed by the measurement. I would say, I cannot tell you much more than this, because at the moment, we don't know when this happens and when this doesn't happen. What I also want to make clear is that factoring is believed to be hard for a classical computer, but there is no proof of such thing. Okay, so what we know is that scientists have been trying to find an efficient algorithm for factoring, and they haven't found it. But there is no proof that this algorithm does not exist.
Okay, I see.
Okay, and so it could be that factoring is easy, and then there was an efficient algorithm for factoring. Okay, this would mean that we could hack our cryptographic schemes already with a classical computer. So the need for a quantum computer would be even, for quantum cryptography, would even more pressing.
I see. And then how could we implement any of these algorithms? So as far as I understand, we have different architectures. Some of them are based on controlling ultra-cold atoms or isolated atoms that we could make them interfere. We could also try to use interference in a photonic chip. What else architecture could we use to implement any of these possible?
I think factoring at the moment is out of reach. So this will be, factoring will be something that we can implement whenever we have powerful quantum computer with error correction. And at the moment, we don't have such a thing.
Okay.
So what we have at the moment, we have some hybrid devices that perform some specific forms of quantum computation. Like there are some machines like D-Wave, for instance, and D-Wave doesn't solve factoring. D-Wave is a specific purpose machine that aims at solving some problems. It's not even clear whether it's better than a classical computer. But we now have some quantum machines where we hope that we can solve some specific instances of problems. But this is at the moment an open question.
Okay. Sounds great. So thank you very much again for your contribution, and I think that it's time to move forward to the next speaker. So thank you very much, Antonio.
Thank you.
So our